Okay, section 10.4 in trig. Let me get a good pen here. Okay, trig. As you saw on page 648 in the class activity, the graph of y equals e to the negative x squared has some interesting properties. I know I just read that off the screen and I don't typically do that, but I just wanted to make sure that I mentioned it's called the parent normal curve. There are some really important points that need to be made about that particular curve, and we will eventually change that curve into something more useful for probability. So we start out by noticing, I'm sure you did when you graphed it, that it is a single peaked bell-shaped curve. You also probably noticed from your graph that the domain was all real numbers. It just kept going and going and going in both directions. And then the range, it only went up to a maximum value of 1. And that maximum value I mentioned a little bit later here, that maximum value occurred at an x value of 0, and that maximum was 1. That's right there in the middle where it comes together. The other details, it's an even function, right? The y-axis cuts it in half, so it's an axis of symmetry. Y equals 0 is an asymptote to the graph, right? The x-axis. And, you know, we also saw in there that the graph changes concavity when x is plus or minus radical 2 over 2. Those are called inflection points. Points where it changes from being concave down to concave up. And you got one on either side. The last and probably one of the more important things is that the area under the curve is the square root of pi. Talk about irrational. Okay, so the parent normal curve has those details to the graph. Now, you want to know how crazy your math teacher is? When driving between Grable and Leo, so on Grable, Leo Grable Road, right? So from Grable to Leo, when you're driving in that direction, you will notice on the pavement where they made a mistake when they were driving the machine that laid down the pavement. And it looks kind of like this. Let me back up a little bit here. So as you're coming down the road, you can see where they went out and then they came back in. And yes, I am crazy enough to think of the parent normal curve or the standard normal curve every time I see it, because I'm a weird math teacher like that. So, whoa, don't zoom out that far. What's this thing called the standard normal curve, and how does it relate to the last one called the parent normal curve? Well, we performed two scale changes, two rather odd-looking scale changes. The first one, we multiply the x's by radical 2. And the second one, we divide the y's by square root of 2 pi. Now, when you do that, you change this parent normal curve to look like this. Y equals 1 over the square root of 2 pi times e to the negative x squared over 2 exponent. That's kind of a weird looking formula. A lot of times you will see it written 1 over the square root of 2 pi e to the negative z squared over 2. And the reason they changed the letter to z is because a lot of times we are dealing with z-scores in probability, and the standard normal curve is perfect for z-scores. And here's the reason why. Because the standard normal curve changes, we call it the z-axis instead of the x-axis, and instead of the middle being some other value, it's 0, and then the units are in terms of z-scores, which we'll talk about more in section 10.5. It is still a single peaked bell-shaped curve, as you can tell. The domain is the set of all real numbers, with the range going from 0 to a high value of 1 over the square root of 2 pi, and I know that looks extremely weird. That maximum value occurs when the x value is 0. It is still an even function. That has not changed. The z-axis is now the asymptote. The points of inflection are a lot nicer than they were before, plus and minus 1. But the biggest and best thing of all of the standard normal curve is that the area under the curve is equal to 1. That is the most important thing about the entire standard normal curve. Well, I shouldn't say the most important, but it's a very, very important point. With that in mind, we can figure out probabilities because we know that the probability of events occurring has to add up to 100% or 1. Just as a refresher on your z-score formula, which we will be using a lot tomorrow, z equals x minus mu over sigma, right, where we're talking about the mean and the standard deviation. Sometimes they use x minus mu over sigma like that, and sometimes you'll see them more generically look at a formula like that. But it's pretty much the mean and the standard deviation which you're using. Whether it's from a sample or the true population average, that's a different question. But in order to find z-scores, we'll be using this same type of formula. And we'll be doing a lot of it in Section 5. See you in class. Oh, and I don't want to accidentally forget the people out there in the world that need me to say their name. You know what? I don't have anything funny to say, Schneider, but you can write this down anyway. Have a great day.